Hello and good afternoon. Welcome to the HiPERFORM Webinar on wide bandgap powered drivetrain for dual in-wheel motors. My name is Christoph Abad and I'm the moderator of today's webinar, as well as the coordinator of HiPERFORM project. Today's webinar will be held by Claudio Romano, Nicola Amati, and José García-Naya. May I introduce them shortly? Claudio is working as a system engineer for Ideas and Motion. Nicola is a professor for driver assistance system design and dynamic design of machines at the Department of Mechanical and Aerospace Engineering of the Politecnico di Torino. And José is an associate professor at University of Colonia, working in the group of electronics technology and communications. Just a few words on HiPERFORM before we start the presentation. HiPERFORM project is funded by Excel Joint Undertaking and also receives support from national innovation programs. HiPERFORM's main goal is the application of wide bandgap semiconductors in automotive applications, be it electrified vehicles or charging infrastructures. Within the project, 31 partners from 8 countries are working together. The project is led by ABL List GmbH and will end this year in October. Today's webinar has the focus on the second, third, and fourth named objective on the right side of this slide, supporting more compact and fail-safe drivetrains, as well as increasing the efficiency of the power electronic solutions. Now I will hand over to the presentation to Claudio. Before we start, I'd like to mention that this webinar is recorded and will be available for later view on our homepage. At the end of the presentation, you will have the possibility to ask questions, which you already can type in during the presentation using the Q&A tab. So I will hand over to Claudio, starting the first part of the presentation. So Claudio.
Okay. Can you see my screen?
Yes, it's fine.
Okay. Thank you very much, Christoph. Thank you, everybody. I am glad to be here to give you a very quick overview about the high voltage dual inverter developed here at Ideas in Motion for the HiPERFORM project. This is the last born of our own family of traction dual inverters, ranging from discrete low voltage MOSFET technology to 1200 silicon carbide modules. Let me first briefly introduce the HiPERFORM use case 4. The focus here is to demonstrate a complete powertrain conceived with the capabilities of wide bandgap materials. The aim is to exploit the benefit of a complete e-axle based on high torque density in wheel motors in combination with a single power unit able to drive both of them. The integrated double inverters has achieved significantly increased level of power density, allowing better vehicle integration with improved efficiency and requiring a simplified thermal system. Also, all the relevant safety life cycle steps pertaining to the whole e-axle system has been identified and executed, leading to detailed recommendation for the implementation of safety mechanism inside the dual inverter unit. As main result of these activities, an operational vehicle prototype with a dual silicon carbide inverter will be evaluated and assessed first in the bench at the test bench and later in a real condition environment. This functional test will provide valuable information for successful implementation of the technology on electric vehicle automotive market. So the focus of this presentation is our wide bandgap powered drivetrain. But first of all, let me spend a few words about the battery electric vehicle and hybrid electric vehicle architecture, which actually represent the target application the dual inverter is tailored for. According to our experience, the general electric architecture of most of these vehicles can be connected to this picture. The central element is the high voltage battery. Most battery electric vehicle and hybrid electric vehicle are equipped with lithium cell, and thus a proper battery management system is required. Then an onboard charger and a DC-DC converter towards the 12-volt network complete the energy cluster. Normally, a body unit takes care about collecting the user inputs and showing essential vehicle information to the driver. In addition, a vehicle management unit is in charge to run vehicle dynamic control strategies, whose scope is to provide the proper torque demand for the powertrain cluster according to the user request and to the vehicle feedbacks. Two different concepts are possible in terms of powertrain architecture. In a central motor architecture, one single motor is connected to the wheels through a gearbox, which is normally include a mechanical differential. The picture here describes a different approach instead, where two motors are directly coupled with the wheels, removing any mechanical link between the active wheels. According to several OEM, there are many advantages to report using this kind of approach in terms of frame layout flexibility, saving in terms of volume and weight, and last but not least, drivability. In fact, most advanced vehicle dynamic control strategies are based on torque vectoring techniques, which intend to apply different torque on each active wheel. In other words, VMU spreads torque over the available wheel motors and thus each wheel needs its own traction inverter. Therefore, in-wheel or near-wheel motor-based e-axle always requires a couple of traction inverters and a management unit. These considerations are the rationale which stay behind the idea to focus on a dual inverter architecture. Here, the aim is to provide a single platform integrating two independent three-phase inverters and an edge technology vehicle management unit. There are at least three aspects to be reported as a key improvement. Well, the first is related to safety, since the generation of motor commands and the acquisition of motor feedbacks of the two wheels are performed by the same computational unit, the system may react immediately, preventing risk in case of any kind of failures of one of the two motors. Furthermore, the integration of the vehicle management unit ensures a safe and low latency channel for torque request, and thus more accurate torque vectoring strategies are possible. Last, this approach allows some cost saving. For instance, the items are actually sharing the same mechanical housing. Now, let's have a look over the main characteristic of the oldest child of our family of dual inverters. It has a plastic shell, but top and bottom aluminum covers ensure proper thermal management and robustness. It can fit shielded cables for both AC and DC power connection. It is liquid cooled and it is allowed to deliver up to 150 kilowatt continuous power for each of the two sections. Well, even if the unit have been designed for a pure electric vehicle, it perfectly fits hybrid vehicle as well. And we should also notice that both in-wheel or emergency multi-phase central motor architecture are supported. Prior to dive deep into the internal structure of the unit, let me just briefly recall the general architecture of a traction inverter. On the 12-volt logic side, the VMU represents the interface between the vehicle and the powertrain. Torque demand coming from the VMU is converted into the equivalent current request according to the proper motor model. Controller compares measured motor current with this set point and thus adjusts the required phase voltage, which are implemented by PWM signals. The picture here shows an insulated architecture. It means that the 12 volt and the high voltage domains are galvanically isolated by the driver board. The next step to obtain a dual inverter consists in double the driver board and the three-phase bridge. The diagram here shows IDS in motion dual inverter general architecture. The logic board is based on the last release Infineon Oryx tricore, and the supply stage rely on Infineon system-based chip. This device, in combination with the Oryx microcontroller, is able to support up to SLD application as a safety element out of context. Furthermore, an FPGA is in charge to monitor driver commands and feedback signals with the target to put the system in a safe state in case of failure. Different recovery action can be taken depending on external conditions. Well, following the path towards the power section, the driver board amplifies commands coming from the logic board to the suitable voltage level to fit power device gate driving requirements. The driver board is based on Infineon coreless transformers isolated driver. For safety reason, each driver has its own isolated power supply. A simple push-pull topology allows to reduce the transformer dimension. Selected driver is one of the few automotive-grade isolated driver available, but it is dedicated to IGBTs devices, so we add some external circuitry to protect MOSFET against short circuit. And now we are further investigating new generation of isolated devices, more specifics for a silicon carbide MOSFET, to simplify or at least to remove this additional circuitry. Coming to the internal structure of the dual inverter, I would say we are using such a Lego approach in which every brick is tightly connected to the others, but can be easily replaced. The power modules are directly coupled with the heatsink. We choose to stay on a widely used packaging solution which integrates 3 half bridge into the same module. Different technologies are available both in standard IGBT or silicon carbide flavor from several suppliers. Infineon names this solution as hybrid pack drive. Its peculiarity is to exploit the benefit of direct cooling with an array of pins directly plunged into the coolant. A single DC-link capacitor is located in the middle of the unit, very close to the power modules. Integrated bus bar have been specifically designed to minimize stray inductance, which is always one of the main constraints the designer must take care while developing. Last, I'm telling you about the phase current sensing. Our design is compatible with automotive off-the-shelf core transducers. This is a standard and reliable solution, but it is expensive and wastes a lot of internal volumes. Actually, this is a backup and benchmark solution to develop a novel sensing solution based on a high-precision coreless sensor. Several technologies are under investigation, but all of them are actually measuring the magnetic field originating from the current flowing through the bus bar. Coming to my last slide, I will give you a very high-level overview on the dual inverter software partitioning, leaving the details to following presentation. Since we are talking about a multi-core microcontroller with 4 cores, in our architecture, 2 of them are dedicated to the motor control, while the remaining 2 cores implement all the vehicle management unit strategies, including advanced torque vectoring controls, which will be detailed later on by Nicola. This structure ensures a very fast and coordinated reaction between VMU and motors controllers in case of failures. Well, we are done with this short overview on the dual inverter application. If you have any specific question, please address them to question and answer section at the end of this webinar, or contact us directly. Thank you very much for your attention. I think now it's time for me to leave the stage back to Christophe.
Thank you, Claudio. So then it's time for Nicola.
Christophe, do you see my screen?
Not yet.
Let me check.
Here we go.
Do you see my screen now?
It's fine.
Okay. Thank you, Christophe. Good afternoon to all people that are present in this webinar. My name is Nicola Amati. I am a professor at the Department of Mechanical and Aerospace Engineering. And today I'm going to present our activity on torque vectoring control for in-wheel motors. This is the agenda of my presentation. After the objective, I'm going to present the controller design, the design of the observer, then the numerical simulations, and then the experimental tests that are ongoing in order to validate our control strategies. What is the objective of this activity? The objective is that of enhance the vehicle dynamic performance by implementing a torque vectoring strategy. Torque vectoring strategy that is possible by the fact that our reference vehicle is based on or is equipped by two in-wheel motors that are driven by the dual inverter described by Claudio before. On the right, you can see the picture of the vehicle that was proposed by the partner JAC, on which the front axle e-motor drivetrain has been substituted by a rear axle based on in-wheel motors and dual inverter. This slide will show the general architecture of the torque vectoring control strategy that is going to be implemented in order to properly allocate the torque on the wheels in order to enhance the lateral dynamic behavior of the vehicle. The control architecture is based on combined kinematic and model-based estimator of the vehicle side slip angle and of the vehicle and of the ground friction coefficient. Then there is a subsystem dedicated to the torque vectoring controller, and then a part dedicated to the definition of the torque allocation on the left and right rear wheels, also taking into account issues related to slippage of the wheels, of the tires. The core of the activity is dedicated to the definition of the torque vectoring controller. Torque vectoring controller that are based on three main contributions. The first one is an adaptive linear quadratic regulator. The second one is a yaw index controller. The third one is a feed-forward controller. We will see in the following slides just some insight about what are the features of them and what are the contribution that each of them will allow for the proper result. So for what the yaw index control is concerned, it is mainly dedicated to the control of the yaw rate. In this case, the objective is that of developing a yaw moment which is proportional to a yaw index, IY, that is given by the error between the desired yaw rate, that is the expected steady state yaw rate, and the measured yaw rate. Then the coefficient KYI is defined on the base of some model equations that are reported here below, but that for sake of don't waste time, will not describe it in detail. The main objective of this type of controller is to improve the yaw rate of the vehicle in order to have a yaw rate that is the expected one that the vehicle would have in case of steady state condition. The second controller that is going to be implemented is a linear quadratic regulator that is based on a single track vehicle model. It is a nonlinear model which is coming out by the fact that the tires have a nonlinear behavior. This means that at each time step, the equations of motions should be linearized, and at each time step, what is defined is the coefficient KLQR that is going to multiply the error between, in this case, the variable which is the side slip angle of the vehicle and the yaw rate of the vehicle. The LQR controller is working in combination with the yaw index controller in order to improve the performance of the vehicle for what the side slip angle of the vehicle is concerned. The third controller is a controller which is a feed-forward control block that allows to improve the sportive performance of the vehicle. In this case, the main objective is to push the vehicle to perform typical performance of a vehicle which is equipped with a lower yaw moment of inertia. So the structure of the controller in this case is based on the desired vehicle dynamics on a reduced yaw moment of inertia. Therefore, from the desired model, desired yaw moment is derived. This desired yaw moment is going to be compared with the yaw rate coming from the actual plant, which is the child of the combination of the controller and the modeled plant and the modeled disturbances. the objective is to minimize the error between the yaw rate coming from the model and the yaw rate coming from the dream model of the vehicle. To develop such a model, it is requested the development of an observer that allows to observe two variables, the side slip angle of the vehicle and the friction coefficient. Among the different approaches that are available on the literature, it has been followed an approach based on the combination of an extended Kalman filter and a kinematic formula. This is the formulation of the extended Kalman filter. This one is the formulation of the kinematic formula. Again, we will not enter in the mathematics of this formulation. The message that we want to pass is that both are fast and their combination allows to have a good estimation of the side slip angle. To confirm this, in this picture, it is reported the yaw rate and the side slip angle that has been obtained by the our estimator, which is the red line, and the which is the red line, yes, in comparison with the green line, that is the result coming from the numerical analysis, which should represent the actual side slip angle of the vehicle in a different operating condition. The difference between the blue line, which is the child of only the extended Kalman filter, and the red line allows to understand what are the benefits of the combination of the two estimators. We are not 100% we don't have zero error with respect to the expected results, but we can demonstrate that this accuracy is to be considered enough. So for what is concerned the analysis of the results, some set of simulations were carried out using a nonlinear bicycle model, which is the reference bicycle model that is at the base of the controllers, and a vehicle model, a complete vehicle model that is implemented in a car sim environment, while the nonlinear bicycle model is implemented in a MATLAB environment. The reference maneuver that was considered is a double lane change, and here we can see some results about the performance of the torque vectoring control at a friction coefficient of 0.8 at 50 kilometers per hour. The red vehicle is the non-torque vectoring vehicle, while the blue one is the vehicle equipped with the torque vectoring. On the right side, we have reduced the friction coefficient of the ground, and in this case, the benefits of the torque vectoring is much more evident. The slide that is reported, the results that are reported in these slides are going to show at the limit condition for the non-torque vectoring vehicle model what are the differences and what are the benefits of the improvements coming from the implementation of the torque vectoring. What we can see in this case that at 120 kilometers per hour and the friction coefficient of 0.75, we are able to improve of 40% in some cases the side slip angle. And in addition to that, improve also the reduction of the steering. These control strategies were tested in real time by a proper code generation and deployment in an Raptor EQ-based, as depicted in this picture. On the left, we can see the flow that allows to upload the code on the and deploy the code on the Raptor ECU, while on the right we can see the structure of the simulation that were run or the experimentation that were run, where in the control unit labeled as 1 is running the controller, while in the displaced control unit, which is labeled as 5, is running the vehicle model. In addition to that, are ongoing some experimental tests that are done in the mechatronics laboratory of the Politecnico di Torino, in which we are going to test the e-axle. In this case, the model of the vehicle is deployed in a Scalexio D-Space real-time unit together with the control of the torque vectoring control. This is the hardware in the loop test bench that was developed by the partner Encopim. It is based by 2 dynos, and on the 2 dynos, by means of a joint and proper torque meters, are installed the 2 electric motors developed by the partners, by the partner Elafe, and the dual inverter developed by IDS and Motion. So the activity that are ongoing are activity in which the vehicle and the controllers are deployed in the Scalexio emulator. By a CAN bus, we are going to communicate to the dyno of the of the rear left wheel, to the dyno of the rear right wheel, and to them we are going to pass the speed reference, because the 2 dynos are emulating the vehicle speed, while to the e-motors driver, to the dual inverter, we are going to pass the reference for the for the rear left wheel motor and the rear right motor. And here on the right, you can see some results that have been obtained by preliminary tests on the torque that is the reference torque which is passed to the electric motors and the reference speed that is passed to the dynos. In this stage, the controller is already deployed on the Scalexio for rapid prototyping reasons. In the last step of the experimental activity, then the torque vectoring will be deployed directly on the dual inverter developed by the partner IDS Emotion, as described by Claudio before. So in conclusion, what I can say is that the numerical and experimental validations that are ongoing are demonstrating the benefits of a rear axle powertrain, which is based on torque vectoring control, silicon carbide based dual inverter, and in-wheel motors. Thank you for your attention, and at the end of this webinar, I will be available for questions. I will now leave the floor to Christoph. Thank you for your attention.
Thank you, Nicola. So then, going to the third part for José. You're still on mute, José.
Can you see my screen now?
Yes, it's good.
So hello to everyone. Welcome to the last presentation of this webinar, which is titled Telematic Control Unit for Wireless Remote Access to CAN bus Data. My name is José García-Naya, and as was introduced by Christoph, I'm with the University of A Coruña and the City Research Center in Spain. The motivation for the telematic control unit, which I'm going to present in this talk, appears when developing and testing automotive parts, as shown in the previous presentations from Nicola and Claudio. And this typically requires access to data which is available on the CAN bus. It's also desirable to be able to access such data remotely instead of recording the data offline and then uploading to whatever system. This also allows to testing in different geographical locations. And even more, it's also very convenient that this data is available on a centralized point, like for example, a cloud, which allows for collaboration between different teams and at the same time and in different locations. The solutions that are available on the market typically are based on closed or proprietary software tools, closed and proprietary hardware and protocols. Some of them do not allow for multi-team remote co-working, and when they do, they are really pricey solutions, and typically they are not suitable for SMEs, small medium enterprises, or modest research groups. The solution that we have developed in the HiPERFORM project is the telematic control unit, and a couple of pictures of this unit are shown here on the left of the slide. It's an R-embedded Linux system. It is autonomous, compact, and cost-effective, and it has the following network interfaces. It has an LTE category 4, which allows for 150 megabit per second peak download throughput and 50 megabit per second peak upload throughput. It also includes an embedded eSIM and also an external SIM. It has also a Wi-Fi IEEE 802.11 network interface, which is a very typical Wi-Fi connection nowadays. An Ethernet over USB, mainly for programming and debugging purposes. And of course, a CAN interface up to 1 megabit per second. Here you can see on the left a picture of the top view of the unit we designed. Here on the top left corner is the daughter board with the hardware for the CAN interface and for the Wi-Fi. This is here the antenna port for the Wi-Fi, also the status LED for the Wi-Fi and CAN devices. Here there are some user configurable button, a reset button, and also an LED for the status of the power of the unit. Here are the elements related to the power supply. On the bottom is the LTE module and the 2 antenna connectors, and finally the main USB port and also a couple of LEDs for the status of the cloud connection and also the CAN receive and send messages. On the bottom view, you see again more elements for the power supply and the external SIM socket. This unit is integrated in the car. Here you can see a picture of the car and an architecture similar to the one shown in the previous slide in previous presentations. It is an electric car with a dual E motor and dual inverter. And the telematic control unit is connected to the CAN bus of the car, and the data is uploaded through Wi-Fi connection, which is especially suitable when the car is in the laboratory or in areas where the cellular network coverage is very poor or almost inexistent. and then the antennas for the LTE connection. Both cases, data is uploaded to the cloud and also allows for configuring and interacting with the unit from the cloud. Once the data is available on the cloud, different development teams can access to the data for different purposes. With respect to the cloud architecture, here on the right-hand side, there is a block diagram of the main modules of the design. At the bottom is the telematic control unit hardware and the telematic control unit communication module, which is responsible for the secure and low-level communication with the telematic unit based on the MQTT protocol. The data is then passed to the message router, which is in charge of interacting with the query module for processing the queries that come from the client for accessing the data directly from the telematic unit, or to pass the data to the CAN decoder module. And this module, based on the DVC information, is responsible for converting the raw data to engineering units. Once the data is converted, it is stored permanently in the persistence module, which is based on InfluxDB database. It is a database specifically designed for time series data. The data available from the CAN decoder module can also be relayed to other clients or even to other clouds. Therefore, you can set up a multi-team collaboration very easily. Finally, there is this graph viewer module, which is responsible for forwarding the data to the web viewer based on Grafana. The unit was integrated into Tecnalia's vehicle simulation framework. Tecnalia is also a partner of the HiPERFORM project. Here on the picture on the left, you can see the driving cockpit with the driver and also the main elements, I mean the steering wheel, the gear selector, pedals, and so on. Then there is the unit graphic engine that you can see the vehicle and the main controllers. Here is the hardware from the Tecnalia's hardware in the loop, 3 screens. On the picture of the right-hand side, you can see a much more detailed description of what is available on each of the screens. And also the telematic unit, which is connected in this case to the LTE external antennas. Finally, there is this laptop here with the basic HiPERFORM CAN viewer, which was developed for this integration, and is showing the data available on the cloud. Therefore, we run the simulation in real time. The data is collected from the CAN bus by the telematic unit, which is uploaded to the cloud through the LTE connection. And finally, it is retrieved from the cloud using this laptop in which HiPERFORM CAN viewer is running. Here you can see on the left a screenshot of the web viewer developed for this integration, whereas on the right-hand side, there is a picture of a new web viewer we are currently developing based on Grafana, which has much more advantages with respect to the basic viewer we had before. Now I'm going to show you a short video of the demonstration of the integration. You can see the basic controls, how the driver is driving the car. The data that is available on the CAN bus. As you can see in the web here, how the data is updated real time. And you can see some sporty driving mode. And this leads to the conclusion of my talk. So we have developed a hardware and a software rich platform. It consists of a telematic control unit plus the cloud solution. It allows for wireless remote access to data from the CAN bus, supports both Wi-Fi and LTE wireless communications. It is an efficient cloud implementation based on MQTT for low-level communications with the telematic unit, and also on InfluxDB database for time series data. Now also has a web viewer based on Grafana, and it is in global, an affordable and portable solution, which enables co-working in multiple clouds at the same time. Currently, we are working on integrating this telematic unit into the demo card of the HiPERFORM project, improving also the Grafana web viewer. As a future lines of work, we have here two examples. The first one is extend the telematic control unit to support additional CAN interfaces. And the second one is also to provide a much more scalable cloud solution, allowing massive number of telematic control units working at the same time. So this is the end of the presentation, and I will be glad to answer your questions at the end. Thank you very much.
Thank you very much, Jose, for the nice presentation. So yeah, you have the chance now to enter questions into the chat or in the Q&A tab. We'd be happy to answer them. So let's give the people a couple of seconds. And maybe one question to Claudio. You mentioned at the beginning, there's the first one, so maybe taking directly this one. So the question is about the switching frequency of the silicon carbide inverter. Claudio, can you comment on that?
Yeah, sure. Thanks for this question. It's a very interesting topic. The current design is able to drive silicon carbide switches up to 30 kilohertz. We are now exploiting the advantages of variable frequency switching technology to optimize to minimize losses, so to optimize efficiency. Up to now, the high level, the high limit is 30 kilohertz. We know that they are pushing higher for higher frequency, but we also know that the limits is not simply the inverter itself, but the limit is on the electrical machine side, because if you go with higher frequency, you need to increase phase voltage slope edges, and this will negatively affect the insulation over the electrical machine. I think this answers the question.
I guess so. So thank you very much. Maybe an additional one. Claudio, do you already have any comparison on the SiC-based version of the dual inverter and the IGBT version you have mentioned during your talk? Do you have any comparisons already?
Yes, we have performed some comparison between our solution with silicon carbide modules and a standard IGBT solution. And in some points, mainly at the low current working points, the increase in efficiency is in the range of 8 to 10%. This is not true if you increase the current, because you are going to use the silicon carbide in a region which is not suitable for silicon carbide. But with the partial loads, the advantage is not negligible.
Okay, thank you very much.
You're welcome.
Are there any further questions coming in on the chat? I hope at least the question regarding switching frequency was answered sufficiently. Okay, well, I don't see any further questions. I just received some thanks for the presentation, so highly welcome. Oh, there's one coming in. I'm interested in the hill bench in terms of replicating the dynamic response of the motors. Are the bench load motors dimensioned to be able to react as quickly as the direct drive motors? Maybe Nicola, can you comment on that?
Yes, the dynos are developed by Encopim in order to have low inertia. They are permanent magnet dynos, and this allows to replicate high dynamics and allows also to replicate the slippage that occurs at the tire ground contact. We have done some preliminary tests. Now the test campaign is ongoing, and I hope that soon we are able to show the results also in limit condition maneuvers.
Okay, thank you very much for the explanation. So, thank you, coming from the questioner. Obviously answered the question, great. So yeah, if there are no further questions, I say a big thanks to all participants joining us today. As mentioned at the beginning, we will put the webinar on our homepage so that everybody can have a look again at the presentations, as well as share it with others who might be interested into these presentations. There are also 4 more webinars which were held over the last weeks, which can be viewed at our homepage. And yeah, so then again, a big thanks to all of the presenters today doing the presentations. And yeah, then I wish you all of you a nice afternoon, and yeah, stay tuned for the final results of HiPERFORM project. Thank you very much and have a nice day.
You're welcome.
Thank
have
you.
a nice day. Thank you very much.
Thank you. Thank you very much. Bye. Thank you. Thank you to all.
Thank you. Bye.